So you have a parallelogram. So this is your region R that you're integrating over. So what's going to happen is, here's our xy plane. We have this mapping between the xy plane and the uv plane, and you need to figure out what region this parallelogram is mapped into. So what you can do is, are you given x and y in terms of u and v, okay. So then what you need to do with this is you need to invert these mappings, so you want u, v as functions of x and y. And the reason why you want that is then you can take all four of these points and plug them in, and that'll show you what kind of region you're mapping into. And that will help you get your limits for u and v. You still need this information. You need this to get your Jacobian of x and y with respect to u and v. You'll include your integral. So once you have your limits in u and v and your Jacobian, then you can so now this will be, we need to go over a new region, R tilde, which will turn out to be much nicer. And then for x, you can fill in what x is. That's your x plus 2y. Okay, and work out all that. Oh, and don't forget the Jacobian. Change of variables problem. For this time, you get to come up with the change in variable involved. X squared plus 4y squared plus 9z squared to the 3/2 dv. Okay. So don't be put off by the 3/2. It's not nearly as bad as you think. So the idea is you want to change variable x, y, z mapping to u, v, w. That makes it nicer because E involves the same expression. It's the ellipsoid bounded by x squared plus 4y squared plus 9z squared, so it's less than or equal to 1. So that defines the entire region. Okay. So here we have an ellipsoid, but it'd be much nicer to work with a sphere, because then you can use what? Okay, in the problem I say equals 1 to denote the boundary of a region. So the entire region is when this is less than or equal to 1.
You just have to form the 9 backwards.
I do?
Yeah, it's 9.
Ah,
Y,
okay.
4 Z.
Right. Okay. Point for you, man.
So my point, I need to donate it to someone, or because my point doesn't go anywhere, right? From today.
Well, how did you decide that, though?
I'll
I'll let you worry about that.
Okay.
All right. So here if you look slope, it'd be nice, much nicer to work with a sphere, because then you can use spherical coordinates, which will make this whole thing work out much more nicely. So, so you can choose the simplest mapping possible to convert this ellipsoid to a sphere. So ideally you want u squared plus v squared plus w squared. So you want to map it to this. So you can just choose however you want to relate x, y, z to u, v, w to bring that about. Because you don't need a mapping like this. Here we have x, y depending on u and v both. The relationships don't have to be coupled. You can have x depend on only u, for instance.
Why did you change it to less than or equal to?
Oh, because E is a solid, I need to include the boundary and interior. So now in the way of a problem, I have E is a solid bounded by the ellipsoid being equal to 1. But here, since I was too lazy to write bounded by, I put less than or equal to account for both the boundary and the interior.
But on the problem, we don't do that.
No. Yeah. So once you make this change, then you can use spherical coordinates, and then this integral looks a lot nicer than it does at first glance. And I think that's it.